Welcome to the Astrophysics Podcast. Let me make something very clear. Black holes are not science fiction. They are real, observed phenomena in the universe. They are one of the most incredible predictions of Einstein's general theory of relativity. The idea is that gravity is able to bend time and space, and when enough matter is densely packed into a small enough region, time and space are distorted so much that it creates what we call an event horizon. Gravity is so strong that nothing, not even light, can escape the black hole. Anything within the event horizon is forced, inevitably, to move towards the center of the black hole, and therefore all of the matter inside is compressed into a single point in space, which we call a singularity. The idea of somehow escaping a black hole would be tantamount to traveling faster than light. The very structure of space and time makes it impossible. It's almost like trying to paddle upstream in a river. Even if you try putting your rockets on full blast and point your rocket ship outward, you find yourself moving backwards, as if dragged by the current back towards the black hole. Arriving at the singularity is inevitable once you cross the event horizon. So, black holes can be really good at eating. But what sort of stuff do they eat? Well, some of the smaller black holes we observe are getting a steady, regular diet of gas, sometimes being fed by a neighboring star at a slow and steady rate. But others are much greedier. In particular, supermassive black holes, millions of times the mass of our sun, live at the cores of galaxies, typically eating whatever gas is accumulated at the center of the galaxy. And sometimes a star gets captured by one of these supermassive black holes, and it gets torn to shreds and gobbled up, nearly all at once. Depending on the black hole, this can produce a really bright event in the night sky that we can see in our telescopes when looking at distant galaxies. We call this a tidal disruption event. It's a really dramatic type of transient explosion that astronomers are now getting a lot better at both observing and understanding. One of the current leaders in improving our understanding of these events is Dr. Brenna Mockler. Dr. Mockler is a postdoctoral researcher at Carnegie Observatories who tries to relate our observations of tidal disruption events to her theoretical predictions. We'll be talking with Dr. Mockler about what black holes like to eat and how we can tell what they've been eating by observing these bright events. I'm Paul Duffel, and this is the Astrophysics Podcast. Welcome to the Astrophysics Podcast. I'm Paul Duffel, and my guest today is Dr. Brenna Mockler, Professor of Physics and Astronomy at... I have something written wrong here. Professor of Physics and... You're not a professor at all. All right, let's try that again.
I was like, wow, thank you.
That's pretty good. I really am doing this blindly. So, let's try that again, shall we? Welcome to the Astrophysics Podcast. I'm Paul Duffel, and my guest today is Dr. Brenna Mockler, who is a postdoctoral researcher at Carnegie Observatories. Dr. Mockler, thank you for joining me on my little podcast.
Thanks for having me, Paul.
So when was? Do you remember when we first met?
Ooh, at Berkeley some point,
okay.
I think.
When I was a postdoc at Berkeley.
Yeah, when you were a postdoc, I was a grad student.
You were still a grad student.
At Santa Cruz. Which is why Abby gets confused and thinks that we might have gone to grad school together.
Oh, okay, because you would, yeah. So that would have been like 2015, 2016 or something like that?
It would have probably been, I would bet 2017 or 2018.
Oh, okay. Well, still quite a while. So, let me start by asking you, where did you grow up? Actually, I can. People who can hear your voice already know it's on the West Coast, but
yeah, it's funny because I just met someone from my hometown in the field the other day, and I could tell from her voice. I grew up in Davis, California.
Okay, and what was that like?
That was very, in retrospect, very lovely. It was very nice. It's a college town. It's very easy to bike around, so you have a lot of, and safe to bike around, so you have a lot of freedom as a kid. Which is nice. So yeah, I just remember a lot of biking around in warm weather and wandering around barefoot on green belts, and it was really pleasant. Right.
So that's where UC Davis is, and it's basically a college town. Is that? And now, was your family affiliated with the college at all, or was it just a coincidence you were?
It was. There? Mostly a coincidence. My mom went to law school at UC Davis, but they were living in Alameda, actually in the Bay Area, when I was born. And then Davis has good public schools. My dad got a job in Sacramento, which is right nearby. And my mom's like, Davis seems nice. So
okay.
They moved back.
Okay, cool. All right. So do you have a memory of like the first time you knew you were interested in science?
It's funny. I was just talking about this, and when I was little, I did not really think of science. I thought space was cool. I thought astronauts were super cool early on. Maybe that was the earliest space thing. Is I have like a little astronaut costume from like elementary school. But I wasn't super interested in science in elementary school. My favorite subjects were math and reading and PE.
Okay. math and reading and PE
were my favorite elementary school subjects. Yeah.
Mm-hmm. And so you as a kid you liked math, but you didn't like you weren't like a science.
I don't think that there was much math in science in elementary school,
right.
And so one of the first science projects that science times I remember really enjoying science was we had some little project. We were making a circuit with a light bulb, and that was really fun.
Yeah.
But then a lot of it, I just remember like drawing pictures of different types of rocks and just being like, this is boring.
That's nuts. Yeah.
Well, geologists would argue that it is, but yeah.
I don't imagine most geologists just go around drawing pictures of, maybe they do. I don't know. I don't know what geologists do with their day, but I imagine it's more than just drawing pictures of rocks.
Yeah, I think it's more than that, certainly. That might be a small subset, but I think it is more than that.
So, so then you got interested.
I think I really got interested in science in middle school because I was lucky to have a couple really, really good science teachers. My first, our middle school was 7 through 9, weirdly. My 7th grade science teacher, Dr. Phillips.
Mm-hmm.
We called him Dr. Phillips. He actually went by Mr. Phillips, but he did have a doctorate.
Okay.
So we would call him Dr. Phillips sometimes. He would just kind of let us. We had a section on like astronomy things, which was really cool. Mm-hmm. And he would just let us ask questions about whatever and just go on random tangents.
Okay.
And so I think we actually had a discussion about black holes in like 7th grade middle school science. Yeah, which is really cool in retrospect.
That is cool.
Yeah.
Okay, so that got you into it is like...
Yeah, and then my 8th grade teacher's motto was a fire a week.
A fire a week.
Which was also exciting.
Okay. So once a week you would come up with some kind of demonstration.
He'd have some demonstration that involved fire.
Okay.
Kept us engaged.
That does keep your kids... Yeah, and the whole week you're like, when are they going to set something on fire? That's pretty good.
Yeah.
So that's how you kind of got in that field. So, and do you feel like your parents were influences on how you got to getting into science, or?
No. I love them very much, and I'm honestly admire what they do because it's just they're both more in like kind of social justice related fields, but neither of them did anything STEM related.
I see.
They're kind of like, this seems cool, but you're on your own, honey.
Okay, so they didn't, I guess you didn't get a lot of like homework help with like your calculus assignment. No, you just did it all on your own. Yes. Okay, that's fine. But so she said your mom was a lawyer.
She's a lawyer, yeah.
And your dad.
He has done a few different things. When I was a kid, he was the director of different nonprofits. Yeah, the Catholic Charities of California. For that, he's not actually religious, but he is culturally Catholic, I guess.
Okay.
And then I think that's something we have in common. Well, I mean, I think you're yeah. And then the Head Start of California, which is like early childhood education.
Oh yeah, Head Start. Yeah.
And he's been more involved. Now he does more consulting things for like early childhood education.
Okay. Okay. You just liked science and just decided to do it.
Yeah, I really liked math. and then and then I got excited about science, but then when I did physics classes in high school, that was my like favorite subject that I thought was most interesting. But it's still in high school, I thought that I might do like environmental engineering or something.
Okay.
That had a little bit more, I felt like more, tangible.
Yeah, when I was in high school, taking physics was like, wow, like, because it was the first class where I was like, okay, all this math I'm learning then gets applied to the real world.
Yeah, exactly.
So I found that to be eye-opening, and I didn't even know what physics was until then. So I kind of it was kind of cool to see.
Yeah.
So then you latched onto physics then.
I think that was pretty similar. Yeah. I remember like a very Davis specific memory of like biking around, and in the fall, like when there's leaves on the ground and stuff, you try to like avoid the leaves because it gets very slippery. And I was like, ooh, I don't want to switch to I was just like thinking about the friction and the different frictional forces and like the coefficients of like like static, which is when the wheel's rolling, versus if it's sliding. And then it's like, and I was like, oh wait, I actually could calculate this. Like this is like immediately applicable.
That's cool. So then, what do you think made the transition towards in the direction of astrophysics?
Yeah, that happened actually late in undergrad. I think I was always interested in space things, but I just didn't really know what that entailed research-wise, like what that would actually look like. And I was doing physics in undergrad at Cornell, and it's a separate department, so there's not as much overlap as there would be in some places, but actually I think it was really I did an REU, not at Cornell, an REU where I worked on some of the detectors for LSST, which was random, but I learned more about cosmology and just telescopes and stuff. So you did an
undergrad, and that was at Davis?
That actually was at SLAC. It was actually technically a Department of Energy.
That's all very funny because you did an undergrad research project at SLAC, so
in the summer
at Stanford.
Yes.
But helping design detectors for LSST.
Yeah.
But then nowadays they do that at Davis, right?
I think so the detector was originally being there is a strong connection with Davis, but they were I don't know exactly the status now,
but it just was a coincidence.
It was total coincidence.
Okay.
I was just trying to get back to California in the summers, and I also didn't have as much time to do research during the school year because I was playing sports.
Okay. Yeah. Okay. And so from some of these undergrad research, maybe this one in particular, you started to be like, oh, I started
learning more about it, and then I started pursuing that more. And the next summer, I did an REU, which was after my junior year, so right before applying, at Santa Cruz, and I met my to-be advisor. And it was very serendipitous because I'd actually met him at a Women in Physics conference at Santa Cruz.
Okay.
This was it winter of my I guess it's been sophomore. No, winter of junior year. That I almost didn't go to because I'd been going to there's these really cool conferences for undergraduate women in physics, and there's a few of them around the country, and you generally go to the one in your area. Okay. But my mom pointed out that I wanted to go to grad school in California, so it would make sense to go to the one at Santa Cruz.
And so you could
I did.
And then she apparently was right.
And she was right.
Because then you ended up meeting.
And at the time, I was like, I don't think I'm going to go to grad school at Santa Cruz, Mom. She's like, there'll be other professors there from there. It's the regional one. And I met Enrico there, and Ramirez Ruiz, my advisor. And he's like, oh, you should apply to this RU program at Santa Cruz. And I was like, oh, I'd specifically looked at that, but I didn't think I was eligible. And he's like, no, you should apply. And so then I wouldn't have applied if it weren't for that. And I really, really loved this sort of research, and like both the way that my advisor did research and also the type of research. I felt a lot more like you're pulling in lots of different types of areas of physics together.
Yes.
and also you can do some order of magnitude calculations to get something interesting.
Yeah. So then, so that's cool. And so, I guess we'll talk more about like what that specifically entails in a minute. But he was doing, what was that particular project?
It didn't end up. It was probably a bit intense for a first project for an undergrad over the summer. It was trying to put IMBHs into an existing simulation of globular clusters in Flash, and I'd never done hydro before.
So there's a lot of things to put together.
So
there was a computational. It was a computational project where you were modeling a galaxy or
a globular cluster.
Right. It was a globular cluster in a galaxy. And then also putting black holes, like what
point sources,
like 100 or 1,000 times the mass of the sun.
Yeah.
And putting that in and seeing how it changed things.
Yeah. And ultimately, what happened?
That's quite a lot for a little summer
thing.
Like, well, maybe try doing this. And seeing. My advisor was the same way, where he's just like, oh, maybe you could try doing this, with no hint as to how hard that would be.
I did learn how to use Flash that summer and like mess around with the code and like change things in it. And I got to the point where I can't remember what I realized about like how I was pretty sure something would have to be completely like remapped to like get the black holes in the right way, or like I was like, oh, I think this could happen this way, but I now no longer have time to do it this summer.
Well, that's a lot of undergrad research projects are like that, right? You just barely start to figure out how you're supposed to do the problem, and then the summer's over.
But
that's fine. But that's how it goes. So when do you think you feel like you first learned how to be a scientist?
I think part of it probably was in undergrad doing like mathematical proofs and stuff. Well, I guess that's one side of it, like how to structure an argument and how to think about like make sure you're carefully thinking through all of the different like holes and stuff in it. That side of being a scientist, I probably I think was probably pretty good at. Now I'm just thinking of a lot of connections to that. Like in high school, I feel like I was always probably like if we had to make some argument for some class or some debate, I would like research every possible like thing that could come up and like know and like
the
probably
entire decision tree.
The entire decision trees would go in. And then I would afterwards have to like take out a bunch of that because it was way too much to put in like whatever I was doing in high school.
Yes. But so you seem to suggest that's not everything it means to be a scientist.
No. Well, yeah. So the kind of like researching things extensively and also structuring an argument, I think there are two parts of it. I think the like figuring out like what questions are interesting and like how to pursue those. I guess that's almost more specific, but that definitely I feel like took until like grad school to really develop.
Yes.
Figuring out what kind of the next questions to ask and what the next projects.
So because your research was a lot of computational projects.
Yeah.
And there's, when you're an undergrad, you can be taught how to set up a problem and hit go, but it's much harder to learn what problem you're supposed to set up. That's
thank you for rephrasing that. That's exactly kind of that part of being a scientist, which is kind of the bigger picture thing, took longer. Although part of that is also it just takes a while to understand the big picture ideas in a field, and that you kind of need that to know what's interesting to pursue next.
Okay, so all right, so now you're an astrophysicist. What are some things that you like the most out of your job?
I mean, whenever you step back and think about what you're actually studying, you get out of like the nitty-gritty details of a problem. It's just so cool that you get to be studying things in space that are actually real. I mean, we're theorists, but we work with observers. And so different and so out there. And it's I like the perspective that it gives on like humanity and like Earth and everything, because it reminds you of like how small and insignificant, and therefore like how important like just like caring about people and things like that are. So like that kind of big picture thing I always really like. More in the details though, I just really, really like problem solving. Like I really like figuring out a math or science problem, just like doing a calculation and seeing that it makes sense and that it works. Just it gives me a nice feeling of accomplishment and is fun.
I totally agree. That's really fun. Is there anything you don't like about your job?
I think I don't think this has to be a part of it, but I think it often traditionally has. I don't like how individual a lot of academic research is. And this is maybe slightly more of a theory thing than an unnecessarily like people who do observations or build telescopes or in other fields do big projects. You have to work with a big team of people. But in theory, a lot of times it's very individual.
Yes.
And I don't think I sometimes need to just be like, sometimes I do want to just get in the zone and like think about something by myself for a while. But then generally I'll like come up for air and I'll want to discuss it with people, and I'll want to like, I need to like kind of ping those ideas off of other people to like even see if it makes sense as an idea.
Yes.
And you can do that, but it doesn't. Oftentimes I feel like the way things are set up at research institutions is it's not quite as conducive to doing that outside of like very regularly. Almost.
Everyone's got their own office and they're doing their own work.
And they're responsible for their own projects. So like, you're like, oh, I have to get my own work done first, instead of like the way I would love it to be is like, oh, I'm working with a group of people on these group of projects and we're all like kind of working on them and I'm doing this thing. And because I'm interested in it, I'm leading this.
And you're right that a lot of research is like that. But if your goal is to be like, to get a big academic position or something, you're supposed to prove that you don't need anybody else, that you're just the leader who's doing things all on your own, and like, and then other people follow you, right? Yeah. And of course that attitude means that you don't. It's holding you back to like just to be collaborating too much, and so which is that's very unfortunate.
Exactly. I think it can be better once you have a permanent position, certainly, but then even so you get to the like you're the kind of head of your own little like sphere, and that's not my ideal setup, I think.
Oh, you don't think so?
I mean, I love having students. I love collaborating with like that's actually one of my favorite things is collaborating with students. But I just don't like the hierarchical structure of it.
Yes. Well, that's fair. I love having a research group, but our group is not very hierarchical.
Yeah. Okay. I love having a research group.
Yeah.
I don't love the way that they're generally structured.
Yeah.
And necessarily power structured, like regardless.
That's kind of unavoidable, right?
Exactly. That's what I mean by it.
Yes, that's true. But okay. So, I guess then what would you say is the most challenging part of getting to where you are in academia?
I mean, I think
it's okay if you don't have a good answer for that.
I mean, I think generically, like getting through grad school is a lot of just like perseverance more than any other thing, I would say. At least like it's just like, there's parts that are gonna be really hard and long and you're not gonna want to do some parts of it, and it doesn't necessarily, I don't feel like it has to be that way as much, but I do think that is difficult. I think
the nature of research often means that there's a lot of time spent just banging your head against a problem. Because, ideally you're in a space where there's lots of people you can go to to talk to about it and that sort of thing. But there's no way around the fact that this is a problem that hasn't been done before.
Yeah.
So, like you're going to you're going to end up spending. It's just going to be. It's a large barrier to get especially when you're learning how to do this.
Yeah, I think it's the banging your head against the wall by yourself aspect that can be quite difficult in grad school. And if you can find people to bang your head against the wall with, that makes it a lot better.
That's good.
I guess that reminds me, I guess the other thing that I felt like I really had to get better at in grad school was just not having very structured schedule or time and building that structure for myself. I think that was a big skill development thing for me.
Yeah, that's right. It's everyone wants to be their own boss, but then suddenly you're like, now you're in your office. Figure out what you're supposed to do, right? And like it's suddenly it's very vague, ill-defined,
and very long-term things too. Like it's one. I think I was very good at being very structured and on top of my time for most of my life, but there were always such shorter deadlines. And then all of a sudden...
this has to be done in a week or something.
Yeah.
And then you'll have all of your problems.
As opposed to we don't know how long it'll take.
Yeah,
that's part of the things you'll figure out.
Exactly. It might take a week. It might take 5 years. It's not... We don't know because we haven't done it before.
Exactly. And it made it harder for that planning part of my brain.
That was definitely... that was... When I was a grad student, that was definitely something I had to learn how to do, was to see, to try to anticipate when something was going to actually take a year to do. My advisor would be like, oh, maybe you could try this. And I go wait a minute.
Yeah.
I know what this is. I know what the rabbit hole you're sending me down. Getting good at, I learned how to do that. But yeah, it is, the learning process involves ending up just doing things that go nowhere for a really long time. All right, so now we're in the part where we're talking about science. Okay. All right, you ready?
Yeah.
All right, ready for the question. When you meet a new grad student or a fellow scientist and they ask you what you work on, what do you tell them?
I generally tell them that I work on high energy transients, especially ones that happen in the centers of galaxies. So looking at the supermassive black hole when it's accreting things. And then All right, that's enough. There's enough words.
Let's start. Yeah, let's back up for. I'll let you continue in a second. So when we'll start with high energy transients. You said.
Yes.
Okay, so when we say transient, we mean
short-lived so evolving on human timescales, and they tend to be much brighter because the energy is spread over a shorter period of time. So there's a lot of power.
So something that's bright in the sky for some period of time,
like weeks to months.
Right. So
maybe days.
The most common example of a transient being a supernova.
Yeah.
Right. Something that's bright in the sky for some period of time. That's like something like a week or maybe something like that. And so, all right, so that's part of it. So you high energy transients.
Yep.
But then you're particularly unlike supernova, which is sort of the most commonly understood high energy transient, you're interested in ones involving black holes.
I tend to do more black hole transients.
Okay.
Most of my research has been on black holes at the centers of galaxies eating stars. But generically interested in accreting black holes as well.
Good. So, and what I love about this is every once in a while I'll see a newspaper article in the Science, and it'll be like, scientists discovered a black hole eating up a star, right?
Yep,
and every once in a while that'll
they
be
get excited.
Which is cool.
Sounds cool.
It's very cool. So that's what you study. You try to understand how black holes eat stars and what that looks like.
Yeah. So they're kind of like for a long time we studied black holes eating gas. They're active galactic nuclei, generally what they're called, AGN. And doing that helps us study the black hole, which is normally black. It also helps us learn about them growing.
Well, that's the funny thing is black holes are often some of the brightest things that you can study.
Yes.
Because if they're eating anything, oftentimes then they emit this bright radiation, not from inside the black hole, but from the gas that's being fed into them.
Yeah. The gas is getting accelerated close to the speed of light, which it would be at the event horizon. And so if stuff is moving close to the speed of light and it hits other stuff, then
you're going to have a bad time.
There's a lot of energy
energy that comes out. And so that's what gives you a high energy transient.
Yes.
Okay. So, all right. So sorry, I cut you off there.
No, that's good.
And so, all right. So black, for a long time, we've understood, like I think maybe over a century, we've been observing these what you call active galactic nuclei.
Yeah.
And we've understood by now what they are. They're a black hole eating gas at the center of a galaxy. But you're saying this is different from that?
This is different. There's probably a gradual transition, but generally when people talk about stars being eaten by black holes or tidal disruption events, which we can get to that in a moment, but stars getting eaten by black holes, they're generally looking at black holes that weren't eating very much gas before, so we couldn't see them. They were still black.
Right.
And then all of a sudden they light up because they're just eating a single star. And then we can know a little bit more about that gas and about the process, because instead of being some nebulous amount of gas that was accreting in the galaxy, we don't know exactly where it comes from exactly. It's right. We have a lot. It's just like a single star that's being accreted. We know about how much gas is being accreted. We know more about the components of it, and it's a little bit easier to model some parts of it because of that.
Okay. Hopefully a little bit easier to model.
More difficult. You can put more constraints on some aspects of it, I would say.
And so then, all right, so that's the kind of stuff the main thing you're known for is studying how black holes eat stars. But so in particular, we should mention that you are a theorist. I know you said that before, but I just thought I'd mention it specifically. Yeah. And so if as a
on the
theorist,
day I'm observing.
Right. Yeah. Tonight you're actually I'm interrupting you as you're doing some observations. But normally you're just doing theory and just trying to understand these things and compute how much how to relate this radiation. So as a theorist, then what does your day-to-day research look like? Like what kind of
Yeah, it depends. I would say an average day where I'm able to focus a decent amount of time on research would be if I'm in the middle. So there's kind of different parts of research. There's like the early part where you're trying to figure out, you have a problem idea in your head and you're trying to figure out if it's interesting. You'll probably do some quick calculations to see if the quantities that you get from that seem interesting. And then one of the next things I'll do is go a step further and maybe code up some stuff to do some more complicated calculations and see if that still seems interesting. And make some plots. And then after that, that might be maybe if you're doing a paper that's mostly analytical, you kind of just expand on that. And but if you do something that's more like simulation based, then it would be thinking about what sort of simulations you want to run that would be interesting.
Okay, so when you say simulation, you have some computer code you put all the ingredients. You say this is where the star is, this is where the black hole is, and then it comes in and then say what happens to it, right?
Yeah.
Okay.
Well, I mean, the stuff I've been doing right now is the aftermath.
So it's not the actual gas dynamics of the star getting eaten.
No, it's the afterwards when the gas is surrounding the black hole, and you're trying to see what light comes out from near the black hole to out through all of the gas that used to be the star, and then all the way to our telescopes.
Okay, so it's not just good enough to simulate how the gas moves around and gets eaten up. You also have to figure out how the light gets out.
Yes.
Because that's the stuff we see is the light, and then you want to be able to relate?
The nice thing about that part, well, the good and bad thing is that you're much more constrained by actual observations.
Oh, okay.
Because if you get something that doesn't look at all like what we see when we point our telescopes at it, then that's probably not a very good explanation of what's happening.
Okay. I guess tell me more about like how do we know, like when we see this bright flash in the sky, how do we know that's a star getting eaten by a black hole? That seems like a detailed story, or I don't know. It seems like a very specific explanation, right?
It is, yeah. And there's still often a lot of debate about it, and some theorists will say that maybe it's just eating some other gas. I'd say that the first thing that makes it different from than many supernova, well, not all supernova, is that it's a bright flare at the very center of a galaxy. So we think that the supermassive black holes in galaxies are, they generally will sink to the bottom of that potential well and be in the very center. And so a supernova goes off wherever the star is, which is all over the galaxy.
Okay.
And there are stars in the very center of the galaxy.
Right.
But but specifically looking for the supermassive black hole doing something, you look at the very center.
Okay.
So that provides a nice cut.
Okay, so that's one thing that sort of indicates it's something going on right in the center, so it has something to do with the black hole at the center of the galaxy.
Another thing is that sometimes there's generally more higher energy radiation coming out than for a supernova.
So like X-rays?
There can be X-rays. It's been confusing why there aren't always from these events. It has to do with the gas surrounding it, probably. There's often a lot of UV. These are generally very, very UV bright objects.
Okay.
More so than most supernova, which tend to be brighter at optical wavelengths. And the reason for that, the main reason is that it's hotter.
See. So the point is, like, an exploding star, you can imagine, gets quite hot.
Yes.
Sure. But it doesn't get quite as hot as gas, like, about to fall into a black hole and colliding with other gas, and that's moving at the speed of light.
Yes.
That gets really, really hot. And so having some, because it's so much brighter in the UV and X-rays, it's telling you that its temperature is much higher.
Yes,
so that's
exactly.
that's one of the ways we can tell that it has to do with that.
And then there's a lot of cool stuff in the spectra. So if you look at the more detailed information per wavelength, how much light is coming out, that tells you information about different emission from different like elements. For example, or different ions of those elements.
And so that tells you what the original star was made out of?
Yeah. So it could in principle.
Okay.
It also tells you about the conditions in the gas, but it certainly, if you have a supernova, then you are actually producing a bunch of new elements.
Yes.
Through the when the supernova goes off, whereas the star getting disrupted, you're probably not doing all this production of new elements. And so you can, for some supernova, there's very clear differences in the spectra from tidal disruption events.
I see. Okay. All right. I just a question that popped in my head. You don't have to have that good an answer for it. But that was
it is very confusing. So people tend to look at a lot of different. First, they check if it's blue, and then they'll check the spectra generally. Okay.
So then, now these things are these gigantic black holes, like whether they're like 1 million to 1 billion times the mass of the sun, and they're just gobbling. I mean, why aren't they just constantly gobbling up stars, or is there just like?
Yeah. So black holes are supermassive, but they're at their supermassive black holes. They're very, very large, but their actual radius. Or I guess if you think of them as a sphere, their surface area is quite small compared to the size of the galaxy. So it's actually very hard to, even if the galaxy is filled with stars, it's very, very unlikely that a star is going to cross that black hole.
Okay. Even one's so huge, it just needs to be...
It's I think the radius of the black hole, the size of the black hole in the center of our own galaxy is maybe like 10 times the radius of our sun or something like that. So it's actually not, I mean, it can be ripped apart by tides at larger radii, which is really what we're talking about, but it's not actually that big of a cross section for those stars to hit.
Right.
So it's unlikely that the star will hit that tiny target.
Right. That makes sense. So, okay, so it needs to be on a particularly special trajectory, and every once in a while a star will encounter it. And then the black hole gets a tasty snack. And so it's kind of wild that we're able to see these kinds of things.
Yeah.
What do we learn about when we what can we so we understand all these, we can learn about the star, I guess, but we also learn about the black holes that they're there. They're these gigantic black holes at the centers of these galaxies.
Yeah. So one of the big questions in astronomy is how did the biggest black holes at the centers of galaxies get so big? Because it's actually hard to explain it, even if you said that they were if they were pulling in gas close to their kind of like the maximum rate they could be pulling in gas over the entire rate of the entire time of the universe. It's hard to explain the largest black holes. And many black holes that we look at today in the centers of galaxies are currently black, and they don't seem to be pulling in gas.
They aren't pulling in gas, right? So not only would they have to, even if they were eating as fast as they possibly could, that still doesn't explain how the most massive ones got here, and they're not constantly eating that much.
Yeah.
So because we see that we can look at them and see that they're not constantly. Not many of them are not. Gobbling up gas. So then, do we have any idea why that is, or is that just still an open question?
Any idea how they got so big?
Yeah. Well, I'm not asking you to.
No. Yeah, no. I was just wondering which of the questions we have going on. So many questions.
That's right.
Yeah, I mean, some of it probably, I don't work on this, but some of it probably has to do with there's different theories for how big they can be at formation. And if, for example, they were able to collapse from massive gas clouds instead of from stars, which we know that supernova, that sometimes you can have an exploding star that actually then doesn't fully explode and forms a black hole at its center, but then it's going to be like closer to the mass of our sun than to the one in the center of the galaxy. Sometimes maybe they could form from much larger clouds of gas, and then they start larger, so they don't have to grow quite as much. Maybe they could break their what we think is sort of their maximum accretion limit, and if they can grow more efficiently than we think they can, or than we generally estimate they could, that would also help. And so one way that these stars, black holes eating stars, is helpful is that even though it's kind of like a small snack compared to pulling in a lot of gas over thousands of years, the rate that you're pulling in the gas during that small snack is actually quite high.
Right. You're eating a whole star all at once.
Instead of spreading it out.
Maybe if you could manage to get a bunch of those events, you could increase the sort of.
Well, actually, I don't know that it would necessarily explain the rate. But it does studying them tells you a bit about that maximum accretion rate.
Okay. And then, I see. And then basically, if you can look at like distant galaxies and look at old black holes in the early universe and see them eating stars, you can see like how big they were back then.
If you see early black holes, and so getting a handle on the amount of black holes at each mass can tell you something about how they grow.
Yes.
So any sort of black hole accretion, whether it be stars or gas, will help you with that.
Yes.
And then stars specifically getting eaten will help you look at black holes that are close to their maximum rate of eating gas.
I see.
And then
and
you
that
can
teaches
try
you
to
about what what happens. When
Yeah, maybe they can't. Maybe we can better understand if they can eat things more efficiently and grow quicker.
Okay. All right. So then let me ask you this. What do you think? What would you say then? Do you have like something you think of as your most impactful contribution, or something you're most proud of, or something you or just an exciting bit of research that you've been a part of?
Yeah, probably my most impactful one was that we had this theory that if the light curves of these transients scaled with if their time scale is scaled with the rate of return to mass to the black hole, then we could get some constraints on the black hole mass from the light curve of these black holes eating stars. And so that's probably the more,
when you say light curve.
Yes. The flare that we get from a black hole gobbling up a star.
Right.
Any sort of is called it's the curve of light that you see in the telescope. Is that helpful? No.
Not really, but that's okay. I'll tell in other words, when you look at it, like basically if you make a plot of, you say like at this time it was this bright and this later time it was this bright and this later time, and you see the plot of that over time, you can see it getting brighter and then dimmer. Well, that graph you can think of as a light curve, because it's the curve describing how bright it was over time. Is that what? Okay. Yeah. No,
that's good. Okay. Thank you. And we do that for all sorts. When
so
we
you're
say
saying so you're saying being able to look at that and say like how long did it take to rise, and then how quickly it decayed, and if you learn that.
How long was it bright for? Is another very maybe simpler way to put it.
Right. So that tells you something about what?
It tells you something about the mass of the black hole.
Okay.
That was gobbling up the star.
Oh, because it tells you something about how long it takes to fall back? Or?
Yeah. So it's telling you if you have... It's basically telling you about the orbits of the gas around the black hole after you rip the star apart, but before you eat it, which is maybe a
good. All right. So maybe we should get into this. So it's not just like the star just shows up, the black hole just gobbles it up instantly, right?
Yeah.
The star will actually in fact, if it did that, we wouldn't really see anything. If it just went inside the event horizon,
it would be bye for the star.
Right. So instead, it's more like the star kind of zips almost right past it.
Yeah.
And then it gets torn apart.
Yeah, so this is like the same sort of tidal forces that give us waves on that influence the oceans on Earth.
Some people call those the tides.
So we have tides on Earth because of the moon and the sun.
Right.
And that's just one side of the Earth getting pulled more strongly than the other side of the Earth.
Right.
And so the oceans are kind of sloshing around because one part of the ocean is getting pulled while the other side of it is kind of getting left behind.
Right. Okay. So those tidal forces that are causing these tides, that are causing the oceans to be a little bit elongated, essentially, with respect to the Earth.
Yeah.
And depending on the phase of the moon, it'll be high tide or low tide. And so that's due to the moon's gravitational field with respect to Earth.
And the sun's.
But for these black holes, it's a much more dramatic story. There's the black hole raises tides in the star, which are obviously way stronger.
Yeah.
And so that actually, and if the star gets close enough, that just doesn't just raise the oceans a little bit; it tears the whole star apart.
Yes. Yeah. So you could tidally disrupt a planet as well, but you kind of have to have the strong enough gravity that and a compact enough physical thing exerting their gravity that you can get really, really close.
Right.
Without bumping into the thing.
So that's one of those things about black holes, is not just that they're like these kind of crazy, mysterious mathematical objects, but they're compact. They're like the most compact thing you can make is a black hole.
Yes.
And so it makes it so that you can get really close to it and experience those strong tidal forces.
Exactly.
Okay, so good. So now, so the star gets torn apart, and then what happens?
Yes, and then the gas is actually from the star is just keeps orbiting the black hole at first because it's not inside the black hole. It got ripped apart outside of the black hole, and so it's on these orbits around the black hole, but it's kind of in streams instead of or one very long stream that's wrapping around instead of in a star.
It's no longer a star.
It's no longer a star. It's gas.
It's now sort of a stream of gas that's sort of orbiting around the black hole.
Yeah. And the orbit of kind of each part of the the star that is now just like orbiting as gas. So I guess the orbit of each part of the gas depends on how close it was to the black hole when it was disrupted, because if you're in an orbit around the Earth, if you have different amounts of energy or at different velocities, you'll be at different orbits, I guess, is the way to explain that. Okay. I don't know if that's helpful.
I'm just glad that there's somebody on my podcast that has more trouble coming up with words than I do. So this is maybe a first. But anyway, but that's okay. No, so you have this. The point is, each of these little pieces of gas is on its own orbit.
Yes,
and so it causes the stream to sort of be what, like.
So it causes the time that it takes for the gas to come back to the black hole is dependent on the orbit of the gas.
Oh, okay.
And so that's why I was trying to get with different orbits, but I probably shouldn't have tried to explain orbital dynamics.
That might have been too much.
Yeah.
But okay. So now now we're getting somewhere. So the thing, because I'd forgotten why we started talking about this. So the star gets all torn apart, and then the gas kind of flies out, but then it falls back.
Yes.
And you're saying this thing that this work that you did was showing that because the amount of time that it takes to fall back depends on the mass of the black hole, that you could use that information to...
Yeah, so it had been predicted that this would be the case, that because the time that the gas takes to fall back to the black hole depends on the size of the black hole, that could be sort of imprinted in the light curve. The what we were talking about earlier, how long these events are bright for could be dependent on how long it takes the gas to fall back to the black hole. Okay. And so my work was the first work that showed that we did see that in the light curves, that the light curves in fact did there were longer light curves from more massive black holes and shorter light curves from smaller black holes.
So when you see how long it lasts, that's telling you basically there's that information about the mass of the black hole is encoded in that.
Yeah. And so there's been some more recently, now that we have more of these light curves of these transients, we've seen more black holes eat stars, and so we have more examples of how long the brightness lasts compared to how massive the black hole is. There's been more kind of examples showing that relation seems to continue to hold, so that's nice.
That's cool. Wow,
I like that.
That's very nice. It's nice when theory can
explain something.
Yeah,
no, it's great. Yeah. So that's probably the more impactful thing. Yeah. And you were asking about, I don't know how much time you were asking about, things we were excited about too.
No,
I don't know.
Okay. That was a great answer. All right. Now I want to ask you the hard question. In your opinion,
oh gosh,
I think we talked about this at the conference. In your opinion, why should we care about astrophysics?
Did we talk about this? Why should we care about astrophysics? Ooh, how spicy of an
You don't have to give a spicy answer if you don't want. But
no, I think okay. I think there's a couple reasons why. I think one is honestly just because it's really cool to understand what's happening with the universe. I think in that way, I think it's very similar to art or something like that, where it's like, no, we don't need astrophysics to like do something like some of our everyday stuff.
Right.
But as humans, we want to interact with the world. We want to understand the world better, and it's beautiful and it's interesting, and it helps us understand our place in the universe. And that's really, really cool. I do think on longer time scales, that's maybe like day-to-day relevance. I do think that like there's been numerous examples of how understanding the world outside of our planet is also important for understanding things on their planet. I think,
yes.
I mean, I think the exoplanet field's probably the most obvious example of that.
So understanding how other planets and other solar systems formed and evolved. Tell us about our own planet and how its atmosphere works and things like that.
Yeah, but if you think that maybe some days humans will leave planet Earth or explore other parts certainly of the solar system, that seems to be most likely to happen soon. Then I think that sort of information is useful on a longer scale. But
sure,
yeah.
Okay. And so
it drives technologies and stuff like that is the thing you'll always hear, which it sometimes does, but realistically, that's not like what we're trying to do.
None of us are here to invent cell phones, yet somehow we just do that accidentally.
Yep. So and the internet, although that was particle physicists.
That was particle physicists. That's right.
They weren't trying to, though. That's the important thing.
That's right. Okay, so what's next on the horizon for you? Like, what are the next big questions you think would be good to tackle in tidal disruption events or transient astrophysics?
Yeah. I mean, on the tidal disruption event side, I do think there's some big telescope surveys coming up that'll see a lot of the sky and get way, way more examples of these sorts of events. And hopefully that will actually allow us to understand get better statistics, get more examples of black holes at different masses and different galaxies. And also more examples of black holes eating gas at different rates. And all of that will help us better understand how black holes grew to be so big. So that was kind of a big picture thing that I think we'll get a lot more information on in the next, 5-10 years.
Okay.
Which is cool.
Yeah.
That's like kind of big thing. One of the kind of like small, or I don't know if smaller, but things that I've been excited about is I've been doing a lot more of a kind of different type of astrophysics than I was doing before. That is actually doing some of the stuff we talked about earlier, simulating the radiation moving through the gas in these sorts of transients, whether they be black holes eating stars or stars exploding. And so I've been thinking more about different sorts of weird examples of transients that I can model and that we're starting to see again with these big surveys that are getting so much more information. So that's another thing that I'm excited about.
I always like talking to somebody who gets excited about who gets excited about using a new code that they've developed. You're trying to convince the general audience why that's exciting, but you just you're really excited about this. I got this code working, and I really want to see what it can do.
Yeah, I can study so many more things this way. Is one reason it's exciting. Another reason it's exciting is just the learning aspect.
But I know from my experience that a lot of it is I just want to play with these toys that I've created.
That's true. The reason, absolutely. We're getting a lot of weird mergers of stars that result in brief flares of light, and we can learn about stars that live in binaries. That's really cool. Weird transients, again, these are short, high, strong, very bright things in the sky that we just don't know where they come from, but they could be from what were we hearing at the conference we were just at? Just different versions of stars exploding with gas surrounding the star ahead of time, and that creates a different signal in your telescope and could tell you something about what the star was doing before it exploded. That's really cool.
Yeah.
All sorts of weird things that we don't understand yet. And I'm excited to get to play around with modeling them.
Awesome. All right. Well, thank you so much, Dr. Mockler, for joining us. I had a lot of fun talking science with you, and I hope you'll join us again sometime.
Wonderful. I had a great time as well. Thanks, Paul.
Well, that's it for the hungry, hungry black holes. No matter how much we study these systems, it still blows my mind that these are real objects in the universe and not just science fiction. So thank you, Dr. Mockler, and thank you to our listeners. We will see you next time. The Astrophysics Podcast is supported in part by the National Science Foundation under grant number AAG 2206-299. If you want to connect more, or if you have astronomy or astrophysics questions, follow me on Blue Sky at paulduffel.bsky.social. The music you hear on the Astrophysics Podcast was written and recorded by Brenna Ashford. You will find it on her album Trotter. All songs are used with permission from the artist and producer. Check out Brenna Ashford's music if you enjoyed it. This podcast is produced in beautiful Lafayette, Indiana by me, Paul Duffel, Professor of Physics and Astronomy at Purdue University.